Good morning, students. We shall discuss orthogonal curvilinear coordinates in this class. So the syllabus goes like this: tangent basis vectors of curvilinear coordinates, then scale factors, unit vectors in cylindrical and spherical coordinate systems, gradient of a scalar, divergence and curl of a vector, Laplacian in these coordinate systems. So there are four quantities which we are going to learn out of this curvilinear coordinate system. Four things. One is gradient, another one is divergence, then next one is curl, then the last one is Laplacian for cylindrical and spherical systems, for a curvilinear system. So this is what we are going to learn. And of course in the syllabus Cartesian coordinate is not here, but however we are going to deal with all the four quantities for the Cartesian coordinate systems too. But the curvilinear coordinate system mainly deals with the curves which are perpendicular to each other. And of course we know coordinate system, Cartesian coordinate system, x, y, z we know already. So which are perpendicular to each other. So we have x, y and z. So they are perpendicular to each other, which is a straight line. So this is a straight line. Whereas here curvilinear coordinate implies that it's a curved one. So curved one, but all the three curves are perpendicular to each other. They will enclose some surfaces. For example, we have now the surfaces are like this. So we have curves. So this is one curve, this is another curve, this is another curve. We have a surface here. This is surface. This is your surface S2. This surface is S1. This surface is S3. Surface S2 and S3 we have a boundary. So it's a curve. For surface S3 and S1 there is a boundary. So that's a curve. And for the surface S1 and S2 we have a line. So we have a boundary. So this is your another curve. But look at here, it meets at the point P. So all the three are perpendicular to each other. So they are curved lines. Of course, they will be very useful in studying shapes and symmetries of some cylindrical or spherical polar coordinates. So with this introduction, let us start the curvilinear coordinates. Suppose three surfaces U1, U2, U3, which are constants, and they intersect at the point P in the region. The values of U1, U2, U3 for three surfaces intersecting at the point P are called curvilinear coordinates. Of course, all the three curves should be perpendicular to each other. Orthogonal curvilinear coordinates are a type of coordinate system in which the coordinate lines are curved but intersect at right angles, perpendicular. So here, see all the three, they intersect at the point P, they are perpendicular to each other. They are at right angle to each other. These coordinates are used in various fields like physics, engineering, to describe position and solve problems involving curved surfaces and geometries, shape and symmetries. Curvilinear coordinates. These coordinates use curves instead of straight lines. So instead of straight lines, so there will be curves to define position in space. Orthogonality. The key feature is that the coordinate surfaces formed by keeping one coordinate constant intersect at right angles, creating a grid. Very important thing is scale factors. These scale factors are denoted as H1, H2 and H3. They relate curvilinear coordinates to the Cartesian coordinates and are crucial for calculations involving vector derivatives, especially gradient, divergence, curl and Laplace. So we are going to get all the expressions for gradient, divergence, curl and Laplace for the curvilinear system. So what are the applications? So in electromagnetism, it is used to solve some problems involving charged particles, electromagnetic fields and antennas. In fluid dynamics, applied in analyzing fluid flow around curved objects or in curved pipes. Then heat transfer, it is used to model heat flow in complex geometries. So now this is a definition for your orthogonal curvilinear coordinates. So we know that the position of the point is denoted by x, y, z for any point in 3 dimension. So this is denoted by x, y, z in Cartesian coordinates in 3D system. These can be related to other coordinates through a set of functional relations. So that means the Cartesian coordinates x, y, z, they can be transformed to a set of another coordinate system. For example, these relations for cylindrical and spherical. For example, Cartesian coordinates are nothing but x, y, z. For any cylindrical coordinate system, we are going to use this set of equations. For any spherical polar coordinates, we are going to use this set of equations. So you have to learn by heart. Okay. So now there is a relation between x and Cartesian coordinate and cylindrical coordinates, Cartesian coordinate and spherical polar coordinates. So that's a transformation. Similarly, we can transform Cartesian coordinate into curvilinear coordinate systems. Okay. Now we will generalize the curvilinear coordinate system. Let us now generalize these relations by introducing 3 new quantities u1, u2 and u3 by writing the functional relationship. So x, which is a function of u1, u2, u3, y is a function of u1, u2, u3. Similarly, z is a function of u1, u2, u3. Similarly, we can transform this coordinate system into another coordinate system. So we can transform, this is your Cartesian coordinate system. So this is your curvilinear coordinate system. Curvilinear coordinate system, see, u1 is a function of x, y, z, and u2 is a function of again x, y, z, u3 is a function of x, y, z. So this is your Cartesian coordinate system. We can transform into curvilinear coordinate systems like this. Okay. The transformation, as I said just now, equation 3.1 and 3.2 gives 1-to-1 correspondence between x, y, z and u1, u2, u3. This represents curvilinear coordinate system, which is a function of x, y, z. This represents Cartesian coordinates, which is a function of u1, u2, u3. I repeat, this is a function of u1, u2, u3. This is a function of x, y, z. Okay, this is curvilinear coordinate system. This is Cartesian coordinate system. We can transform one system into another system, like we have transformed, see, one system into another system. This is for the cylindrical and this is for the spherical. Cartesian coordinate into cylindrical, Cartesian coordinate into spherical. So similarly, we can transform from curvilinear coordinates into a Cartesian coordinate and from Cartesian coordinate into curvilinear system. So it implies that any point can be labeled either by the coordinates x, y, z or u1, u2, u3. So it can be labeled x, y, z or u1, u2, u3. The values u1, u2, u3 corresponding to a given point, the point where it meets, where it interacts at the point P, are called curvilinear coordinates of P. Equation 3.2 defines a curvilinear coordinate system. So as I said earlier, so this is for the curvilinear coordinate system and this is for the Cartesian coordinate system. So geometrically, the transformation from Cartesian coordinate system x, y, z may be viewed as a mapping from the Cartesian space to curvilinear space. Let us choose now u1 equal to c1 as a constant. So where it interacts. So as I said earlier, there are two surfaces. They will interact with the point. They will interact with the line C u1, which is equal to c1 as a constant. So u1 is a function of x, y, z. So u1 is a function of x, y, z, which is equal to c1. This is a constant which is represented in a diagram as s1, surface s1. Similarly, u2, which is a function of x, y, z, which is equal to c2, and c2 is a constant which represents s2 surface. Similarly, u3 is a function of x, y, z, which is equal to c3, which is nothing but your s3, which is surface s3. These surfaces s1, s2, s3, they intersect at the point P, whose Cartesian coordinates x, y, z can be obtained by solving the above equation 3.3, 3.4 and 3.5 easily. So meaning of orthogonal curvilinear coordinates. As I said earlier, u1, u2, u3 are coordinates for the curvilinear coordinate system. So they are nothing but continuously differentiable functions. u1 equal to c1 is a constant, u2 equal to c2 constant, and u3 equal to c3 constant. They are all coordinate surfaces s1, s2, s3. The intersection of two surfaces at a point defines a coordinate curve through the point. The intersection of two surfaces This is the intersection of two surfaces. This one. Similarly, these two surfaces they intersect like this. Similarly, we have two surfaces, they intersect exactly at the curve U2. So the intersection of surfaces S2 and S3. S2 and S3. This is for S2 and this is for S3. The intersection of these two surfaces intersect at the point at the curve U1. So U1 coordinate curve. Similarly, the intersection of surfaces S3 and S1. You have S3 is here, S1 is here. They intersect at the curve U2. So U2, they intersect the curve U2. Similarly, the intersection of surfaces S1 and S2. S1 and S2, they intersect at the line U3 coordinate. Cartesian coordinate system, the I goes from 1 to 3, that is U1, U2, U3. Curves are not straight lines, they are curved. They are not straight lines. Okay, they are curved. That's why the scale factor H1, H2, X3 exists. For this reason, the direction of curvilinear coordinate axis are determined by drawing tangent to the coordinate curve at the point. So we are going to draw the tangent line. See, we are going to draw a tangent line. So we have U1, U2, U3 are the three coordinate systems for the curvilinear. Just to draw the tangent, this is your tangent. Just to draw the tangent, this is your tangent. Just to draw the tangent, this is your tangent. These tangents, they represent unit vectors. So unit vectors E1 is the tangent of U1. Unit vector E2 is a tangent of U2. Unit vector E3 is a tangent of U3. So E1, E2, E3 are unit vectors along the tangents to the coordinate curve U1, U2, U3 respectively. And of course we know about this one. So divergence. So this is for curl and this is for divergence. So divergence, the rule goes like this. I dot I, J dot J, K dot K. So something like that. So we have here it is see here E1 dot E2. I dot J equal to 0, I dot I equal to 1, J dot J equal to 1, K dot K equal to 1, whereas I dot K, I dot J will be 0. So similarly here also the same rules follow for the divergence. E1 dot E1, E2 dot E2, E3 dot E3 equal to 1, whereas E1 dot E2 0, E2 dot E3 0, E3 dot E1 that will also 0. This is for the divergence rule and this is for the curl rule. So similarly I cross J, that will give you K, I J K, I cross J, that will give you K, J cross K will give you I. If it is in a reverse one, it will be minus 1. So you have to remember. So similarly here also we have now E1 cross E2. So E1 cross E2 will give you E3. E2 cross E3 will give you E1. This is exactly like cyclic permutation. 1, 2, 3. So E3 cross E1 will give you E2. Just tell me what is the value E1 cross E3. Anyone? E1 cross E3. Minus E2. E2 is correct answer, but with a minus sign. It goes in a negative way. Okay. So you have to follow only permutations. 1, 2, 3. Is it okay? So this is for the curl, then this is for the divergence. As I said earlier, because this is curved, you have to follow only certain scaling factors, and or otherwise we call it metrical coefficients. So it is defined as H1 equals your mod of dr by du1. So you have to remember. Okay, H1 is the scale factor, which is defined by this. H2 is defined by this mod of dr vector divided by u2, where r is a position vector xy plus yj plus zk. Okay, so now H3 is given by this, and of course dr by du1 equal to I times dx by du1, j times dy by du1 plus k times dz by du1. Suppose we are going to take the mod. When you are going to take the mod, so when you are going to take the mod, you will have to take the square root, take the square and take the root. So now you will have to take the square root and take the square. So that will give you dx squared by du1, dy squared by du1 whole square, dz partial dz by du1 whole square. We know u1 is equal to x, u2 equal to u1 equal to x. So again x. So dx by dx. So we have now dx by similarly for H2 also. Similarly for H3 also. So we know already. Okay, we are going to substitute for x here. We will see later. Okay, H3 also is given by this. And we know that dr by du1 which is equal to dr by mod of dr by du1 with the unit vector. Okay, you have to remember. This is dr by du1 which is equal to h1 equal to h1 dot e1. So this is defined as h1. Okay, so dr by du1 which is equal to h1. See, we know already this is h1. So h1 dot e1. Similarly, dr by du equal to h2 dot e2. dr by du3 equal to h3 dot e2. So you have to remember all those things which will be using later in the problems. Now, e1 equal to dr by du1. So in a position vector in curvilinear coordinates, it is r equal to u1 e1 vector. Like position vector for the Cartesian coordinate r equal to xi plus yj plus zk. And here it is, instead of x you have to substitute u1, instead of y you have to substitute e1. Is it okay? This is your e2 and this will be your u2 and this is your e3 and this will be your u3. Is it okay? So r equals xi plus yj plus zk for the Cartesian coordinate. Here it is r equals u1 e1, okay, e1 cap. Similarly u2 e2 cap plus u3 e3 cap, where e1 is given by this, e1 cap is given by this. So e1 cap, see here, e1 cap is given by this. So e1 cap is given by this. Your e1 is here. See here, e1 cap is equal to 1 by h1 dr by d1. I repeat, e1 cap equals 1 by h1 times dr by d1. See here, e1 cap equals 1 by h1 times dr by d1. dr by d1 is e1. This is e1, this is e1 cap. Don't forget. Okay, we have already defined this. So your unit vectors in the curvilinear coordinates are given by this expression with the scale factors. Scale factors are h1, h2 and h3. Now the infinitesimal vector displacement. So this is for your vector displacement and this is for your surface and this is for volume. Expressions for line element, expression for area, expressions for volume for curvilinear coordinate systems are given by this slide. So this slide brings out the fact of one is line element, second one is area and third one is volume of curvilinear coordinate system. Line element is given by, so we know already line element is given by this. So your infinity, so this small element is given by, you will differentiate. So that will give us dr equal to partial dr by d1. So this is the original definition for any differentiation. Definition for differentiation. So partial dr by d1 plus partial dr by du2 plus dr by du3. dr by du1 is given by e1. So instead of this you can substitute e1. d1 is here. Similarly you can substitute for e2. d2 is here. Similarly you can substitute for this one is e3. Correct? So which is equal to d1 e1. What is the relation between? We have now e1 equals h1 e1 cap. Correct? See. Okay. So we have now, so instead of e1 you have to substitute h1 e1 cap. Instead of e2 you have to substitute h2 e2 cap. Instead of e3 you have to substitute h3 e3 cap. So this is for the line element. Okay, line element. And this is for the area. For area, line element multiplied by line elements. So dr multiplied by dr. So dr multiplied by dr. So that will give you this. This multiplied by another one. This dot with another one. This dot with another one. So dr dot dr. Correct? So we know that ds squared equal to line element multiplied by line element. Length multiplied by length will give you length squared. Area. So here it is dr dot dr. So that will give you area. So this multiplied by another the same thing. So this is dot with another dot. So we have now e1 dot e1 that will give you 1. So this one multiplied with the same thing, that will give you h1 square du1 whole square. Similarly, another one will be h2 square du2 whole square plus another one is given by this. So adding all those things will give you area, infinitesimal surface element, and this is your line element. And whatever for the volume element, for volume element, for any vector vector identity, we have used A dot B cross C. For any vector, A dot B cross C will give you volume element. Okay, A dot B cross C will give you volume element. And of course, this is a scalar. So we'll have only scalar. A dot B cross C. B cross C will be a vector, and this vector dot with another vector will give you scalar. So the answer will be a scalar. So we have now, so this is your the first one, this is your second one, and this is your third one. What is this one? D1 E1. See, D1 E1, D1 E1, and this must be D2 E2, and this must be D3 E3. Now we can pull D1, DU2, DU2, D3 out. Okay, the remaining one will be, you have, so instead of E2, you substitute H2 E2 cap. Instead of E3, you substitute H3 E3 cap. Okay, is it okay? Instead of E2, you substitute H2 E2. Instead of E3, you substitute H3 E3. Now E2 cross E3. What is E2 cross E3? This H2, H3 are scaling factors, scale numbers. What about E2 and E3? E1. E1 dot with E1. 1. Very good. So answer will be H1, H2, H3, D1, D2, D3. So the answer is here. It's a scalar. E2 cross E3 will give you E1. E1 dot E1 will be 1. So answer will be the remaining one. So this is the volume element. So this is your line element, surface element, volume element. Now very important thing is Cartesian coordinates. So next we are going to calculate four identities, four properties. One is gradient, another one is divergence, third one is curl, the last one is Laplacian. For all the three coordinate system, Cartesian curvilinear coordinate system, cylindrical curvilinear coordinate system, spherical curvilinear coordinate system. So this is what we are going to discuss. Okay, four properties. What are the four properties? Gradient, divergence, curl, and Laplacian. Okay. Now expression for gradient, divergence, curl, and Laplacian operators for Cartesian coordinate system in curvilinear coordinates. And of course we know already u1 equal to x, u2 equal to y, u3 is for z. For any curvilinear coordinate system we know already. And this one also we know, h1 equal to mod of dr by de1. So which is given as dx by de1, dy by de1, dz by de1. Okay, so we have now u1. Instead of u1 you can substitute x. Instead of u2 you have to substitute e1, substitute x. e1 substitute, you have to substitute x. dx by dx answer will be 1. Here answer will be 0. Here answer will be 0. So the answer, total answer will be 1. So we have now for Cartesian coordinate system h1 equal to 1. Very important one more question. For any Cartesian coordinates h1 equal to 1. Similarly h2 also will be 1. h3 also will be 1. So h1 equal to h2 equal to h3 equals 1 for Cartesian curvilinear coordinate system. Is it okay? Very simple one. See, h1 equal to, expression for h1 is given by this. You substitute for u1, substitute for u2, substitute for u3. You will have h1 equal to 1, h2 equal to 1, h3 equal to 1. Here also see you have h2 equal to dr by du2. You will have du2, partial dr by du2. You can have dx by du2, dy by du2, dz by du2. So this one will become 0, this one becomes 0, this will become 1. Similarly for the next one, h3 equal to partial dr by du3. du3 is nothing but z. So 0, 0, 1. So you will have h3 equal to 1. So very important one, h1 equal to h2 equal to h3 for rectangular, for Cartesian coordinate curvilinear system, h1 equal to h2 equal to h3 equal to 1. Okay. Now, what are the differential operators we are going to have? One is, as I said earlier, gradient, divergence, curl, and Laplacian. So before that, we need to have some scalar functions and vector functions. We need to have certain things we will be using only scalar functions. For certain things we will be using only vector functions. For example, gradient. See, we have just to take gradient, we will be using only scalar function. For divergence, we will be using only vector functions. So we need to know about scalar function and vector functions. Consider three mutually perpendicular coordinate surfaces described by u1, u2, u3 for any curvilinear coordinate system. And of course, scalar function depends on u1, u2, u3 scalar function. Similarly, vector function also depends on u1, u2, u3 but in an increasing manner. Okay, so this is your scalar function and this is your vector function. Both depend on u1, u2, u3. Both are functions of u1, u2, u3. Now, these are all unit vectors. So, these are the unit vectors along the directions of increasing u1, u2, u3 respectively. Then, any vector A can be defined as like this. We know already that in ordinary Cartesian coordinate system, we know that A vector is AI. Can you remember A1 I vector plus A2 J vector plus A3 K vector. So, similarly here it is A1 E1 cap, A2 E2 cap plus A3 E3 cap. So, this is for the curvilinear coordinate system. The first thing is we are going to discuss gradient of a scalar function. So, gradient of a scalar function phi is a vector whose magnitude and direction give the maximum rate of change of scalar function. So, this is nothing but d phi by du1. Your del phi is nothing but d phi by du1, d phi by du2, d phi by du3. There in Cartesian coordinates, this is defined as d phi by dx. Can you remember? This is d phi by dy, d phi by dz. But here it is u1, u2, u3. So your del phi is defined as in curvilinear coordinates. Your del phi is defined as 1 by h1 d phi by du1 e1 cap, 1 by h2 d phi by du2 e2 cap plus 1 by h3 d phi by du3 e3 cap. Just now we learned that h1, h2, h3 all are equal to 1. So all are equal to 1. Correct? And what about u1? u1 equal to x, u2 equal to y, u3 equal to z. You substitute, you will have del phi equal to, instead of e1 you substitute I, instead of e2 substitute j, instead of e3 just substitute k cap. So you have ordinary way. This is ordinary Cartesian coordinate. This is Cartesian coordinates in curvilinear system. This is in terms of x, y, z. This is in terms of u1, u2, u3. Is it okay? So we can have from one system to another system. This is what I said about curvilinear system. We can transform one system into another system. So we can transform from ordinary Cartesian coordinate system into curvilinear coordinate system. We can transform from curvilinear coordinate system into Cartesian coordinate system. Is it okay? So this is for the gradient.